Molecular orbital theory is the last bonding theory that we're going to talk about. And the difference here, as the name suggests, is that here we're looking at orbitals for the entire molecule instead of for individual atoms. Even for a simple diatomic molecule, it's impossible to solve the Schrodinger equation exactly. So they basically take guesses. So you have a guess called a trial function, and you stick it in there, and you see how that works, and then you adjust it as needed until you get the lowest energy. And they, of course, use computers to do that because the math is pretty complicated. So they optimize the trial function for the lowest energy, and that's what we use to describe these molecular orbitals. Of course, we can never do better than nature does at minimizing the energy of the orbital. These molecular orbitals, we're going to look at LCAO molecular orbitals. That stands for linear combination of atomic orbitals. It's a weighted linear sum of the valence atomic orbitals of the atoms that are in the molecule. This is the simplest trial function that works reasonably well. And so what this does is it combines the valence atomic orbitals of all the atoms in the molecule together. In valence bond theory, we were looking at the central atom and the atomic orbitals on that atom, and we were hybridizing, combining those orbitals, but they stayed on the atom. Right? Here we're taking all the valence orbitals in the whole molecule and combining them. So you can imagine how that could get a little bit complicated. So many of these linear combinations of atomic orbitals are delocalized over the entire molecule. So instead of being isolated between two individual atoms, they're spread out over the entire molecule. Whereas in valence bond theory, the hybrid orbitals remain localized. So here we're talking about delocalized orbitals. That's why they're called molecular orbitals instead of atomic orbitals. So we're just going to look at some simple molecules. H2 is about the simplest you can get. 2 hydrogen atoms, total of 2 electrons. So if we look at the valence electrons, the only electrons for hydrogen, they're occupying the 1s orbital. So each hydrogen has a 1s orbital, and we're going to look at how those orbitals could combine. We're going to do an equally weighted sum because the atoms are the same element. And so we're taking these two and adding them together, and what we get is something that looks like this. Now, you may say, well, how does that work? Well, remember that these are essentially standing waves, right? And so it's a 3-dimensional standing wave, and so it's hard to get our minds around that. But we saw how 2-dimensional waves could interact, and they could interact constructively or destructively. Remember the guy with the balls bouncing them on the pond? And we saw those patterns. So it's like that, but just we're not going to worry about not being able to understand it. We're just going to say, well, it's reasonable. So if we take these two and combine them together, we get this orbital. This is a bonding orbital because it lowers the energy. So this is the original energy of the individual orbitals, and when they combine, the combined energy is lower. So here, as always, we're indicating that energy increases as we're going up. Yes?
Is that because they had to lose energy to combine? Or is it just because like they give off energy to combine?
Is it because they had to lose energy to combine? That's a good question.
It's like they can use energy to
Right.
combine.
Well, oppositely charged things are attracted to each other, and so that attraction draws them together, and the closer they get, the lower their energy is. It's a little bit like dropping an object. You hold an object at shoulder height and you drop it. Up here it has high potential energy. The closer it gets to the ground, the lower its potential energy. So I guess we could think about this, that when these come together, now they have lower potential energy. There's less potential for them to do other things or to come closer, if that helps. We can also combine these in a negative way, a destructive interference. It's like subtracting. It's adding a negative. These orbitals have phases because they're waves, and waves have phases, right? And so if we add the negative phase to the positive phase, that's the same as subtracting the two. And you might say, well, why isn't that 0? That seems reasonable, but it's just more complicated than that. So when these get added out of phase, they're going to cause destructive interference, essentially, and we're going to get something that looks like this, where there's a node in the middle. There's an area in the middle where there's 0 probability of the electron being. And on one side, we have a region of probability that has a positive phase, and on the other side, around the other atom, we have a region that has a negative phase. Just like when we look at standing waves on a string. So here, if we have a string and we start wiggling it up and down, we can get a standing wave. This would be positive phase, and this would be negative phase. So here's the positive phase and the negative phase. It's just a bit more complicated than a piece of string. So backing up for a minute here. This is given the notation sigma. It comes from s orbitals, and it makes a spherical shape. So you're like, well, that doesn't look round. It's actually more of a cylindrical. I just said that differently. So imagine standing down here and looking down the length of that. What would it look like? It looked like, the end of a sausage, right? It'd look round, just like the sigma. So we call that a sigma bond, and a subscript 1s to indicate that that's the combination of 1s orbitals. Oops. This one is also spherical. So if you imagine, standing here and looking this way, you're going to see the end of this, and it's also going to look spherical, right? Oh, that's not very good spherical. So it's also a sigma orbital. But this is higher in energy than the original orbitals. In order for a bond to form, the resulting molecule has to be lower in energy. So the first bond is a bonding orbital. It promotes bonding. This is an anti-bonding orbital. We have electrons in here that raises the energy of the atom or the molecule, and so that works against bonding, hence the name anti-bonding. So we call this sigma star 1s. We use an asterisk here to indicate that that's an anti-bonding orbital. So here's both of those possibilities shown together. So here's a 1s and a 1s, constructive interference. We get something like this, sigma 1s. Those same two orbitals with destructive interference, think of it as adding a negative or subtracting, however works for you. And we're going to get something like this, which does not promote bonding. This is an anti-bonding molecular orbital. Any questions yet? Yeah. So this isn't illustrating relative energy, but we could make it do that. So if energy is increasing as we go up, the original orbitals would be somewhere in the middle there, and so these would be higher in energy, this one, and that would be lower in energy. So we combine two orbitals, we get two orbitals. One's higher, one's lower in energy. Any other questions? So instead of trying to draw weird balloon shapes, we go back to our orbital diagrams and our little boxes containing electrons. So this is a molecular orbital diagram. And as always, we show energy increasing as we go up. Here's the atomic orbital for a hydrogen atom. The 1s sublevel has one orbital. It's just a box, right? And it's got one arrow in it for the one electron. Over here's the other hydrogen atom, also one box, the 1s. Here we've drawn this electron upside down. It doesn't actually matter how you draw it, but when these two electrons come together, they will spin pair. And so we're just kind of anticipating that by drawing that one upside down. The combination of these two orbitals gives us a bonding orbital that's lower in energy and an anti-bonding orbital that's higher in energy. So this part in the middle, these are the molecular orbitals. And when we put the electrons into the molecular orbitals, we follow the same rules and patterns that we did when we were filling up just regular standard atomic orbitals. So the electrons will fill up the lowest orbitals, lowest energy orbitals first. We talk about something called bond order, and this is just kind of a made-up quantification, like oxidation states or formal charges, to help us predict things. So let's go back to this so we can look at it. The bond order is going to be the number of electrons in bonding orbitals. So that's these guys down here. Those are in bonding orbitals. So there's 2 electrons in bonding orbitals minus the number of electrons in anti-bonding orbitals. There aren't any. There's 0. So 2 minus 0, and then we're dividing by 2, and so that is going to equal 1. Why divide by 2? Well, I think it's because we have 2 atoms combining. So for H2, the bond order is 1. And the way the bond order works is if that bond order is positive, that predicts that a chemical bond will form. If it's 0 or negative, then a bond will not form. And the larger the positive number, the stronger the bond is. Okay? So let's look at 2 helium atoms making a molecule. And you might say, well, they're not going to do that. Well, you're right, they're not going to, but we can look at what would the molecular orbitals look like if they did this. So here's the atomic orbital for one helium atom, the atomic orbital for the other helium atom. To make molecular orbitals, we're going to combine those two. We get a bonding orbital and an anti-bonding orbital. Okay? And then we have a total of 4 valence electrons in this He2 molecule, 2 electrons from each. And so when we put those electrons in, we put 2 in the bonding, the lower energy one, and then we put 2 up here because we have 4 electrons. Now when we look at the bonding order, we've got 2 electrons in the bonding orbitals, and we have 2 electrons in the anti-bonding orbitals. So we have 2 minus 2 divided by 2, so 0. So the bond order here is 0, which predicts that this will not form, and it's not stable. Any questions? Yeah. Pardon me? The dividing by 2, where does that come from? Excellent question. It comes from the definition of bond order. So think of it like an average. I think the 2, I'm not positive, but I think the 2 here is because we're looking at a diatomic molecule. So We're doing this for 2 atoms, and so we're going to divide by 2. We're not going to look at anything above 2 diatomic molecules, but the bond order for a larger molecule would probably involve dividing by 3 or 4 or whatever. So that's where the 2 comes from. It's just a way that we can compare the likelihood of this molecule forming, the strength of its bonds, without doing crazy calculations. Any other questions? Well, what if we had He2 plus, an ion, 2 helium atoms bonded together as an ion? The positive charge means they've lost an electron, right? So the original atomic orbitals would be, here we have a helium atom, and then over here, this one would have to be a helium ion, because if we're counting up the number of electrons, we have 2 helium atoms. They each have 2 valence electrons, and the positive charge says I have to subtract an electron, and so that gives me 3 electrons. So combining 1s orbitals, again, I get the same thing. I get a sigma 1s and a sigma star 1s. Now when I put the electrons in, I only have 3 of them, so 2 of them go down here and the third one goes up there. Now when I calculate the bond order, I have, that's the anti-bonding, and here's the bonding, right? So the number in bonding orbitals is 2 minus the number in anti-bonding orbitals, and then I'm going to divide that by 2, and so I'm going to get 1/2 as the bond order. This is predicted to exist, and it does. You're not going to find it in the air. It's going to be under extreme situations, extreme conditions, but it does exist. Any questions? Because after this, we have to get into the p orbitals. So just summary of what we've talked about so far. We are approximating molecular orbitals as linear combinations of atomic orbitals. As with valence bond theory, the number of orbitals that we form combining stuff has to equal the number of orbitals that we started with. So you could think of that as conservation of orbitals, right? You can mash them around, you can mix them up, but you still have the same number of orbitals when you're done. Whenever you combine 2 atomic orbitals to make 2 molecular orbitals, one will be higher in energy and one will be lower, because one will come from constructive interference, lowering the energy, and the other will be destructive interference, raising the energy. When assigning electrons to the molecular orbitals, we fill the lowest energy ones first with up to 2 spin paired electrons. We follow Hund's rule. When we have orbitals with the same energy, we put a single electron in each of them, and then we pair them up before we go on to the next higher energy. And then to have stable bonds, we have to have a positive bond order, meaning there are more electrons in bonding orbitals than there are in anti-bonding orbitals. That tells us this will be lower in energy than the 2 atoms by themselves. So use molecular orbital theory to predict the bond order in H2 plus. Is that bond stronger or weaker than the H2 bond? So the good news is I am not going to make you draw these things on an exam. Okay? If you go and look at the practice exam, you'll see that the questions asked here give you a molecular orbital diagram, and you have to maybe put electrons in it to answer the question, but you don't actually have to draw this. So that's something to be thankful for, right? So energy increasing as we go up. This is a 1s, and this is a 1s. And when these combine, they're going to form 2 orbitals, one lower and one higher in energy. Okay, so one will be lower in energy and one will be higher in energy. And so this one will be called sigma star 1s, and this will be called sigma 1s. I'm not good at dotted lines. So atomic orbital, molecular orbitals. So we're looking at H2 plus. There's some really weird molecules and ions we're looking at here. Well, there are two hydrogen atoms. They each have one electron, right? And this overall is a positive charge, which means I have to subtract an electron. So I only have one electron. So I'm going to draw this one as the hydrogen atom. And this one over here is going to have to be a hydrogen ion that has no electrons. The part on the side here is just the regular atomic orbitals, sort of as an illustration so that we can see where did the molecular orbitals come from. So one electron, when I go to fill up my molecular orbitals, I put one electron in the lowest orbital, and I'm done, right? So it says predict the bond order. Well, the bond order is going to be the number of electrons in bonding orbitals, right, which is 1, minus the number of electrons in anti-bonding orbitals, 0, divided by 2. So that bond order is 1/2. Any questions? So that's the first part here. Use the molecular orbital theory to predict the bond order. Bond order is 1/2. Is the H2 plus bond stronger or weaker than the H2 bond? Is its bond order higher or lower? Well, maybe we remember that we did H2 earlier. Maybe we don't remember. Well, what would be different about H2? You have 2 electrons, right? So for H2, we'd have an electron here, and then we'd put 2 electrons in, and we're going to end up with 2 electrons there. So I'm doing them kind of fat and in purple because that's for the H2. So for H2, we have 2 hydrogens. They each have 1 electron, and so there's a total of 2 electrons. And the bond order for that is going to equal the number in bonding orbitals, 2, minus the number in anti-bonding orbitals, 0, divided by 2. And so the bond order for that one is 1. So which bond is stronger, H2 or H2 plus? H2 is stronger. This bond is has a higher bond order. This one's stronger. The question is asking, is H2 plus stronger or weaker? This one's stronger, so that means the H2 plus is weaker, right? So the answer to that is it's weaker. Okay, so if H2 plus has 1 electron, why are there 2 red electrons here? Is that what you're asking?
Because for the H2, which is in purple, then you put 2 in, but the other H2 plus only had 1, and yet there's still 2.
Okay, so these are atomic orbitals. So these are the atoms before they combine. So this hydrogen has 1 electron. And this is the other atom before it combines. And the part in the middle is the molecule. So this electron is getting drawn twice. Once over here because it's coming from this atom, and once over here because that's where it's going in the molecule. The purple here is when I made it into hydrogen H2 instead of H2 plus by making an extra electron. So let's undo the purple. Actually, do this. So that's back at what we were originally doing, H2 plus. Here's how we figured out how many electrons are in the molecule. This is the molecule in the middle. This is, we're taking one atom or ion and another atom or ion. This is what we've got, and we're going to bring them together, and the molecule is what's in the middle. So any arrows, any electrons that are over here will get moved into here. And anything over here will get moved into there. Does that make sense? Yeah.
I get that part. I get that there's two that are coming together to make a molecule, but we have H2 plus has one and H2 has two, and yet so there's still the same number of electrons in there. Should there be 3 electrons?
So this is H2. Let's see.
We're not combining H2, we're combining hydrogen and hydrogen to get H2. Is that what you're asking?
Yeah, so this is H2 plus. Okay, we're taking H and H plus and combining them. Okay, thank you in the back. When I look at H2, then I have to put another electron in here because now I have an H and an H coming together to make H2. Does that help? Is it working now? Okay. These diagrams can be very confusing, right? Especially when we're first learning about them and we're like, what the heck am I looking at, right? Anybody else have any questions? Because it's easier to get stuff cleared up now before we get into p-orbitals as well. Thankfully, we don't have to do d orbitals. Yeah. Why are there no electrons in here? Because I'm going to put my electrons in the lower energy orbitals first. And so for the H2 plus, I only have one electron, and so I put it in here. I'm not going to put it in a higher energy orbital. It only goes in one place, yeah. So we're counting the number of valence electrons just like we did for all the other things, right? Like for Lewis theory, we learned how to count valence electrons. So we're counting the number of valence electrons, and this part on the side, the atomic orbital business, is not really important. It's the molecular orbitals in the middle. And so it's how many valence electrons do I have? I draw the molecular orbitals, and then I put them in. And I put them in starting at the bottom, and then I move up as needed. So this is like a different hotel. Like we took 2 hotels and combined them together, and now the floors and the rooms and stuff are all different. But the people are still going to choose to stay in the cheapest rooms first, if that helps. I guess we don't have to get to P just yet. So we just covered diatomic molecules of the first period, hydrogen and helium. And so we're going to move on to period 2, the second row in the periodic table. So if we look at Li2, you're like, well, that's weird. Yeah, it is weird. 2 lithium atoms. They're metals. Why would they combine? Well, we don't have to worry about that. Here we are looking at valence electrons, right? So this lithium atom has 1 valence electron. It has a total of 3 electrons, but the other 2 electrons are in the first level those don't participate in bonding. So we're only looking at valence electrons. Everybody okay with that? So lithium has one valence electron, and another lithium atom has one valence electron, and we're going to take the two atoms and make a molecule out of them. And so together we have two valence electrons. So the orbitals combining the 2s and the 2s will make a sigma 2s and a sigma star 2s. Again, two orbitals from two orbitals. We put the electrons in the lower one first, and so they both fit into the bonding orbital. We can calculate the bond order. How many in the bonding orbitals? 2. These guys down here. How many in anti-bonding orbitals? 0. Divide by 2, and so that equals 1. Bond order of 1. Molecular orbital theory predicts that this exists, and it does in the gas phase. Let's look at Be2. So Be2, we have 2 beryllium atoms. How many valence electrons does a beryllium atom have? 2 valence electrons. There's no charge here, so we're not going to add or subtract. And so here we have 4 valence electrons. We combine the 2s orbital from each atom to make molecular orbitals, sigma 2s, sigma star 2s. And we put 4 electrons in here. So 1, 2, and then we have to go up here, 3, 4. All right? So then the bond order, how many in bonding orbitals? 2. How many in anti-bonding orbitals? 2. Divided by 2 is 0. Bond number in the bonding orbitals minus the number in the anti-bonding orbitals, and take the average. So it's 0. Bond order is 0. This shouldn't exist, and it doesn't. It's not stable. Any questions?
It says that is non-stable because the bond.
It's not stable because the bond order is 0. When you form this molecule, there's no benefit in energy. So it doesn't lower the energy at all, so there's just no motivation for it to do this. To get into boron, then we have to look at the p orbitals. So in a way, the p orbitals are more confusing, but in a way they're less confusing. So, kind of break even on this. So each atom has 3 p orbitals along the x, y, and z axis. And just for consistency, we're going to define this axis that goes between the 2 nuclei as x. We'll call that x, and we'll call the other 2 y and z. So we're first going to look at the px orbitals. So they're along the x-axis, and so these are going to overlap end to end, much like the sigma bonds we saw in valence bond theory. It's easier to see the phase in a p orbital because one lobe is positive and one lobe is negative. So when we combine these constructively, we get a bonding orbital that's lower in energy. And we see we have a lot of electron density here between the atoms, pulling them together. And here the electron density is larger away from the atoms, and there's actually a node in the middle where the electrons cannot be. So this is anti-bonding. If we stand at the end and look down, this is also going to look round from the end, right? And if we look down the end of this one, it's going to look round because we're looking at like the end of a sausage. So these are still called sigma orbitals because they have a spherical, cylindrical, I should stop saying spherical, a cylindrical shape. They're round on the end. This is sigma 2p because it's made from 2p orbitals. And this is sigma star 2p. Or what about the other two orbitals? Well, those are perpendicular. So here's a py orbital along the y-axis, and here's a py orbital on the other atom. And when we combine these, again, we can combine these constructively or destructively. Constructively, we're going to end up with something like this, and destructively, we're going to get something like this. The bonding orbital gives us electron density increasing between the atoms, between the nuclei, and the anti-bonding ones increase electron density away from between the nuclei. If we look down the end of this one, it's not a cylinder anymore, right? It would kind of look like two cylinders, perhaps. It'll look like this. But it's not symmetrical anymore. So this is a pi overlap. It's a pi orbital. And this is like the pi bond that was formed in valence bond theory, right? Where we have a side-to-side overlap to form a bond. Here, when we're combining atomic orbitals to make the molecular orbital, we call this a pi orbital because it comes from the same sort of a thing, side-to-side overlap. So this would be pi 2p and pi star 2p. Yes? Yes, what do the colors signify? The colors here are signifying the phase of the orbital. So with a wave on a string, if that's the middle point, the wave goes above and it goes below. And so this would be the red, and this would be the blue. Positive phase and negative phase. So when we combine simple sine waves like this, if the peaks line up and the troughs line up, we got constructive interference and the wave gets bigger, right? And if we line these up so the peaks and the troughs match each other, so I've got a blue one and a red one, then they canceled each other out and there was no wave at all, right? So here, when we line these up so that the blue overlaps with the blue, the positive with the positive, and the negative with the negative, we get a shape that looks like this. When we subtract them or add them out of phase, we end up with something like this. Does that help? A little bit? The PZ orbitals are going to do the same thing. They're just at a right angle. So we're representing the z-axis as going up and down on the screen. So here's one p orbital and another p orbital. And again, they can overlap side to side in a positive way and make this. Or they can combine side to side in a negative way and make that. Yes? How come they flip? That's a good question. I don't know. Yeah. Yeah. The problem with this topic is we are skimming the surface, and we're talking about this at all because we need to get to a point at the end of this lecture that is important for organic chemistry, understanding resonance stabilization. Valence bond theory, Lewis theory, Vesper theory don't handle it. Molecular orbital theory explains what resonance is and how it works. So we have some questions, but we can't go down that far because then we'd have to go into a whole bunch of other things. And honestly, I learned this stuff, I'm sure I learned this in physical chemistry when I was in college, but I haven't done anything with it since. And so all I remember is the stuff I teach you, right? Because I don't have to do anything else. Well,
because pretend you're doing the standing wave
Mm-hmm.
again, and if you put two of them together, they
It's hard, right?
Yeah, I get the concept. It's
Mhm.
hard to explain.
I guess what we're doing is we're looking at both ways that they can combine. They can combine in a positive way. They can also combine in a negative way. And that explanation says, well, why do we show both? They would have to do one or the other. Well, actually, they do both, right? It's like, the electron is a particle and the electron is a wave, and we don't like that, but we just have to go with it. So they do this. And thinking about standing waves on strings, I think gives us enough understanding that we can see, well, yeah, I guess that could be possible. Do I understand exactly how or why it works? No, I don't. And I choose to be okay with that. Because we could find out more, but it's just not that interesting to me. And I'm sure it ultimately wouldn't be to you either, unless you're destined to be a physical chemist. Okay, so did I skip something? No. So when we overlap p orbitals, we have 3 p orbitals from each atom, and we're going to end up with a total of 6 orbitals. We're going to have bonding and anti-bonding orbitals. Some of them are sigma, some of them are pi. So just to make things more interesting, it's actually just because this is how it is. This is the typical energy ordering. The sigma 2p that's the bonding orbital, that's an end-to-end overlap. That's the lowest energy. And then the bonding with the side-to-side addition is the next highest. And then after that is the anti-bonding coming from the side-to-side orientation. And the highest energy is the sigma star, which is the destructive interference end-to-end. That's the typical ordering. But then boron, carbon, and nitrogen have their orbitals in a different order. So just ignore this side for now. This is the expected order. So here we see the s orbitals from 2 atoms, and those combine, and we get sigma and sigma star. Here are the p orbitals that we were just talking about. When you take the px orbitals, those are going to interact end-to-end and form a sigma 2p and a sigma star 2p. And then the other 2 that are along the z and the y-axis, perpendicular to that internuclear axis, are going to make pi orbitals, and we're going to have 2 pi bonding orbitals and 2 pi anti-bonding orbitals. Because we had a total of 4 orbitals interacting, so we need to have 4 orbitals being formed. Yeah, so the order filling here is you put electrons in here first. These are the same in energy, and so you'd go 1, 2, and then 3, 4, and then you'd go into these guys. Okay, so that's what we expect. And if you think about how they're interacting and how they're combining, this end-to-end combination interacts more strongly, right? And so the low gets lower, and the anti-bonding, the high, is higher. And these guys in the middle that are adding side to side, that interaction is not as significant. And so we do have these pi and bonding and anti-bonding orbitals, but their energy differences aren't as great. And so this is what we consider normal. Boron, carbon, and nitrogen do it differently. And the way we remember that is be careful now. Be careful now. B for boron, C for carbon, N for nitrogen. What happens here, the 2s business is the same. The difference up here is that the order of these 2 bonding, or the order of the bonding orbitals is switched. So the order of these is flipped compared to the ones over here. Okay? And it is significant. Why does it do that? Well, this is the book's attempt at explaining that. For boron, carbon, and nitrogen, we get an increase of S and P, X mixing together. So we're adding the 2s orbitals and we're adding the 2px orbitals, but they get mixed up with each other a little bit. And the mixing is greater for these three elements than for these. And so that's what makes the order switch. And that's kind of like just to say, there is a reason. Go on with your day. Okay. So these are the rest of the period 2 elements as homonuclear diatomic molecules. We're not showing any of the atomic orbitals here, the things that we're combining to form the molecular orbitals. What we're seeing here is just the part in the middle, the molecular orbitals. So if we think about boron 2, so boron has 3 valence electrons, and if we have 2 borons, then we have 6 valence electrons. And so we fill these in 1, 2, 3, 4, 5, 6. These are the same in energy, these 2 orbitals, and so they'll fill separately first. Then carbon, we're adding 2 more electrons, and those are going to go in here and fill this up. Nitrogen each has 5, now we've got 10 electrons, and so the next electrons will go up here. With oxygen, we have 12 valence electrons, right? So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. The order here is switched from those guys. Now we're into regular interactions, regular order. And then fluorine, we're adding 2 more electrons, and neon 2, we're adding 2 more electrons. And so you can calculate the bond order for each of those. And you see the bond order over here goes 1, 2, 3, and then it starts to go back down to 1, and this bond order is 0. And then we also have bond energies and bond lengths down here. Notice for the Ne2, there's none listed because that bond doesn't form, so we can't measure it. As the bond order increases, the bond energy increases. The bond gets stronger. And the length of the bond gets shorter. Any questions? Remember? Yeah, go ahead.
Does this have anything to do directly with like the triple bond that occurs in nitrogen in the Lewis model?
That's an excellent question. Does this have anything to do with the triple bond that we saw in nitrogen in the other theories? I'm not sure. Yeah, I don't know. Well, it is. This is shorter and stronger, and so the bond between them, we saw with the triple bond should be shorter and stronger. But I'm not sure. Well, I don't know. I just really don't know. It's an excellent question. No one's ever asked that before. So we've been looking at the period 2 homonuclear diatomic molecules, and that's just quite a mouthful, right? Period 2, second row on the periodic table. Homonuclear, meaning the nuclei of the 2 atoms are the same. They're the same element. Diatomic, there's just 2 of them, and they're making a molecule. So this is, the B2, C2, N2, O2, those guys. And so we can look at the molecular orbitals and use that to explain some anomalies that we observe in paramagnetism. So if we look at the Lewis structure for oxygen, do you see any unpaired electrons? No, they're all paired up. We have lone pairs, and we've got pairs and double bonds. Here's the valence bond theory representation of oxygen. We have the single bond, the sigma bond here, and we have the pi bond above and below. Do you see any unpaired electrons? No, because when these half-filled orbitals overlap, the electrons pair, right? So based on both of these theories, we would predict that oxygen is diamagnetic, meaning all of its electrons are paired up. It's not attracted to a magnetic field, right? Let's see. Come on. So I don't think that was the beginning. Yeah, I guess it was. Okay. Sorry about that.
So, we're going to take this oxygen gas, pass it through this copper coil that's immersed in liquid nitrogen. The liquid nitrogen will condense the oxygen into liquid oxygen, which we can collect here in this pre-cooled door. We will then take the liquid nitrogen and pour it between the poles of this magnet. We'll pass the oxygen also, pour it through the poles of the magnet. And then we're going to see if there's any difference between liquid nitrogen and liquid oxygen.
All that bubbling is because it's the warm copper coil is making the liquid oxygen boil, the liquid nitrogen boil. It's nice passing the oxygen through there, and as the oxygen gas goes through that very cold environment, it condenses, and we're getting liquid oxygen. And that tube is so cold that water from the air is freezing on it. It's frosting up. So it's nitrogen. It looks like water, right? Clear liquid, just pours right through. And the oxygen is sticking. It's getting stuck in the magnetic field. Liquid oxygen is paramagnetic. Lewis theory, valence bond theory says no, it isn't. Yeah, but look, it is.
It only has magnetic as a liquid.
No, I think it's probably paramagnetic as a gas as well, but really tough to demonstrate. Yeah. It's a very strong magnet. Very strong magnet. So we just saw evidence, at least on video, that liquid oxygen is paramagnetic. And we looked earlier at these models and everything's paired up. This is the molecular orbital diagram for oxygen. And look, here in this pi star 2p pair of orbitals, those two electrons are unpaired. If we look at nitrogen over here, all of nitrogen's electrons are paired up. That's why nitrogen just poured right through. But the oxygen sticks because these unpaired electrons are attracted to that magnetic field. Questions? Draw a molecular orbital energy diagram and determine the bond order for the N2 plus ion. And then there's a bunch of questions. Okay, well, let's try to do this. So for nitrogen, our valence electrons are in the second level, right? So we're going to have 2s orbitals and 2p orbitals. So I'm first going to just draw some boxes to represent nitrogen's atomic orbitals. So it's got p orbitals there. And this other nitrogen has some p orbitals and an s orbital. So N2 plus. Well, I have two nitrogens. They each have 5 valence electrons. And then the positive charge means I've lost an electron, so I subtract 1. So that's 9 valence electrons. So then if I'm going to look at the combination of two atoms or ions, I'm going to have one that's a nitrogen atom with 5 electrons and one that's a nitrogen positive ion with 4 electrons in order to get the right number of valence electrons, right? And so then we could put those in here. 1, 2, 3, 4, 5. 1, 2, 3, 4. So we have the correct number of arrows in our diagram. These are atomic orbitals, and then we're going to show how the molecular orbitals form, and then we're going to move these electrons into the molecular orbitals. So atomic orbitals, atomic orbitals. Well, when the s orbitals interact, we're going to make 2 orbitals. And so there should be sigma star 2s and sigma 2s. When we overlap the p orbitals, we're going to have a pair of sigma orbitals and 2 pairs of pi orbitals. The highest order never changes, so I'm going to start up there. The highest one is the sigma star 2p. The next highest is the pi star 2p. And then it's these guys here that can change. This is nitrogen. Are we going to use the expected order or the be careful now? We're going to use be careful now. So what that tells us is that the pi bonding orbitals for this one are lower in energy than the sigma bonding orbital. I should have a 2p. And then I'm only going to attempt to draw all the dashed lines on this side. Because I've got my sigmas and pi's over here, and it just gets really, really messy. So these are the molecular orbitals. 9 electrons. I'm going to put 9 electrons into this center section. I'm just going to fill from the bottom up. So 1, 2, 3, 4, 5. Now this guy's going to take his own orbital because it's the same energy. 6. Now they have to pair up. 7, 8, 9, done. So I drew an MO diagram for N2+. It says determine the bond order. Okay. Bond order is the number of electrons in bonding orbitals. It's a little more involved here. This is a bonding orbital. These are bonding orbitals, and this is a bonding orbital. So 1, 2, 3, 4, 5, 6, 7. 7 electrons in bonding orbitals. Oops. And how many are in antibonding orbitals? Just the 2 there. So 7 minus 2 divided by 2 is 5/2, or 2.5. Any question? So I did that, and I got the bond order. Do we expect this bond to be stronger or weaker than the N2 bond? Well, if I were to make this into N2 from N2+, I'd have to add an electron, right? I would add that 1 electron in here. Is that adding to a bonding orbital or an antibonding orbital? It's adding to a bonding orbital, right? So that's going to increase the 7 to an 8. That's going to make the bond order larger. Does that make sense? If I was adding into an antibonding orbital, that would be making this 2 larger. I'm subtracting, I'm making the bond weaker, the lower bond order. Yes? Yes. So the question is, why is this 2 boxes instead of 3, right? Because when we looked at the overlap of those p orbitals, the 2 that were along the x-axis overlapped end to end, and they made a sigma orbital. And that's a different energy than the pi ones that were combining side to side, because it combines more effectively. And so then the good one is lower in energy, and the bad one is higher in energy than the other ones typically. Does that help? Yeah. So if I'm comparing this to another atom or it would have to be a molecule. If I'm comparing this to another molecule, I look at, well, what do I have to do to make that other molecule? I have to add a bonding electron. That would make the bond stronger. So that means that the N2+ is weaker than the N2 molecule.
Those are 2 separate. Or is that still just 1?
2 separate.
Like the one at the bottom.
This?
That's different than the one on top, right?
No, this is all the same. So if we look at just one nitrogen atom, and go back to familiar things. See, now these old orbital diagrams seem kind of friendly, right? You're like, oh yeah, the good old days. So how many electrons did the nitrogen have? It had 5. 1, 2, 3, 4, 5. This s orbital is a valence orbital in the nitrogen. And that's the orbital here. It's going to interact with the 2s orbital from the other atom.
You just do it separately.
We do it separately because these are always going to be lower in energy, because they overlap better. They combine better. Yeah. So when we draw a diagram like this, if you went into D, heaven forbid, things would get really, really tall, right? And it's all one molecule. We have one more question to answer here. Is N2 plus diamagnetic or paramagnetic? So we're looking here to see, are all the electrons paired up? No. And then we have to remember which is which, dia, para. So confusing. Di means 2. Noah took the animals 2 by 2, right? So diamagnetic, they're all paired up. This is not diamagnetic, so it's got to be paramagnetic. So this molecule would be attracted to a magnetic field. Any questions?
This is kind of off topic a little bit, but do core orbitals ever hybridize or combine?
That's an excellent question. So do the core electrons and their orbitals ever get involved in this? I don't know, honestly. My guess is that if they do, it's very minimal, because it's generally the valence electrons. Those tend to be farther from the nucleus, and so those are the ones that are going to be closer to another atom. Those are the ones that are going to interact more strongly. But as we get a picture with this molecular orbital theory, some of the other stuff that we've talked about is really, really simplified. It's like we use generalizations as facts for small children, right? And then we grow up and we realize, well, yeah, but that's not actually always true. Sometimes there's this, and it gets really complicated. And so here we're getting a picture or a peek into the complicated part of it. Yeah. And what's the point of looking at this at all? Is so that we can understand the behavior of the atoms. So you're probably not going to go into molecular orbital theory again. But we need to have the idea of this so we can understand things like, why is liquid oxygen paramagnetic? Well, molecular orbital theory shows that it's actually a little more complicated, and there are unpaired electrons. What about heteronuclear diatomic molecules? Well, we're just barely going to talk about those. This is the diagram for no nitrogen monoxide. And so here we're looking at the nitrogen atoms, atomic orbitals, and the oxygen atoms, atomic orbitals, and they're not at the same energy level. The oxygen's atomic orbitals are lower in energy than the nitrogens. Don't ask me why, please. And so when we combine these, then, they're not exactly the same as they would be if it was 2 nitrogens or 2 oxygens. The lower energy atomic orbitals contribute more to the bonding orbitals, and the higher ones contribute more to the anti-bonding. Here's looking at 2 even more dissimilar elements, hydrogen and fluorine. Here's hydrogen's 1s electron, and here's the 2p electrons for fluorine. Fluorine is so electronegative that its 2p orbitals are actually lower in energy than hydrogen's 1s orbital. Well, it seems like that should be wrong, but it is what it is. So here, the 1s orbital from hydrogen is interacting with the 2p orbitals from the nitrogen, and how does that work? Well, we can form a sigma bond and a sigma orbital and a sigma star orbital from the px that can overlap with the s orbital. But then what about the pz and the py? Well, they can't overlap with anything, and so here they sit unchanged as non-bonding. They don't contribute, but they don't fight against it. So there's, another thing that can happen.
So they're not anti-bonding,
Yeah. They're not for or against, they're abstaining from the vote, right? So we're here, but we're not going to participate in deciding. Yeah. I don't want to do that one. Okay. Polyatomic molecules. So, resonance. We looked at ozone, and for the Lewis structure, we learned that we can draw two equivalent structures, the difference being where the double bond is. And the double-headed arrow here says these are resonance structures. The true structure is a combination of the two. It's not going back and forth between these. It's a combination, but we can't really draw it, right? The closest we could get is we could have a single bond between each of these and say, well, there's an extra half bond on each side. How does that even work, right? It doesn't. Valence bond model doesn't work for this either. So here we have the single bond, the sigma bond between the two oxygens, then we have a pi bond. That's the double bond. Here's another oxygen, and it's got just a single bond. And so again, we're stuck with having a double bond and a single bond, when in actuality the two bonds are equal. They're equal in length, they're equal in strength, there's no going back and forth. They're a combination. So these theories don't work here. In molecular orbital theory, we can spread that orbital over the entire molecule. And so we can, excuse me, we can have a molecular orbital, come on, pointer. So with molecular orbital theory, we were and ignore that. It's the computer being dumb. We can take one bond and spread it throughout the entire molecule. So this is a pi bond that's delocalized over the entire molecule. Because the three atoms combine all of their atomic orbitals to make molecular orbitals, and those can be delocalized. And so in molecular orbital theory, we can understand how those two resonance structures actually represent something that's in the middle. We can actually describe what's in the middle. This is as close as we're going to go to actually describing it. So we don't want to do molecular orbital diagrams for three atoms. Any questions about this one? And then this is the part that's important for organic chemistry. So benzene is represented in Lewis theory this way. Benzene is C6H6, and it's a hexagonal ring of carbon atoms that are bonded together, and then each carbon atom has a hydrogen atom bonded to it. And the best Lewis theory can do is to have alternating double and single bonds around this ring, and then you can draw the other version where you just switch the positions of the double and the single bonds. The actual structure is a combination, but Lewis theory can't draw that or represent that. This is the molecular orbital representation of that. So that bond, those bonds that we can't place, because in these other theories, all of the electrons are localized. They're on this atom, they're on that atom, or they're between these two atoms. In molecular orbital theory, we can delocalize them. And so those are going to form pi bonds above and below the plane that the carbons are in. And all of these bonds are identical. Each carbon is identical in its experience of bonding to the other carbon atoms. Benzene is very symmetrical. All the bonds are identical. This causes benzene to be much more stable, lower in energy than you would expect from looking at other factors. And so this resonance stabilization is something that becomes important in organic chemistry. Now, do you have to understand exactly how it works? No. but you have to be able to say, oh yeah, there was that thing called molecular orbital theory, and somehow magic, the electrons can be shared over the whole molecule or over this part of the molecule. Okay, I'll be okay with that. That's what we're going for here. Okay? Any questions?